Okay, so now I want to talk about some strategies for developing supervised learning methods and decision rules. And specifically, I want to talk about two different types of approach, what's sometimes called the generative approach and what's called the discriminative approach. Okay, so before we do that, we just want to quickly recall what we know about the decision theory perspective. So the decision theory perspective essentially tells us what the right thing to do is if we knew what the joint distribution of our x's and y's was. Remember, y is the outcome, x is the predictors. If we knew the joint distribution p of x and y from which those were being drawn, then we could develop the optimal decision rule based on computing the conditional distribution of y given x. So if we knew the joint, we can compute this conditional. For example, recall that if you're using a loss function that measures error using the squared difference between your estimate and the true value, then the optimal decision rule is to just use the conditional mean of y, sometimes the posterior mean of y given x. Okay, so we know what to do if we know what the joint distribution of y and x is. But we don't know that in practice. We just have a training data set. So we're going to assume that the training data set is a sample or a set of samples from that joint distribution. Okay. So now there are two different approaches that we can use to learn a decision rule from that training data. The first, which is called the generative approach, is essentially to try to use the training data to learn that joint distribution, p of x, y. If we can use the training data to learn that model, then we can simply, having learned that or estimated it or fitted it, we can just compute p of y given x from the learned joint distribution. Right? So we're going to use it, training data to learn the joint distribution and use that to compute the conditional distribution. So if y is discrete, for example, then learning p of y is fairly easy because it's just some probability on each of the discrete possible values. So in that kind of setting, usually p of x given y is the hard part. So we learn p of y, that's easy. If y is discrete, relatively easy. If x is high dimensional, though, p of x given y might be hard. But just to give you one example, maybe you think that the x's, maybe they're continuous predictors and they're correlated with one another in some way. So you might fit a multivariate Gaussian model to x given y. So that would be this Gaussian models within classes. Another thing that people sometimes do is, even though x may be correlated, but modeling those correlations can be hard if things are in high dimensions. So another thing that people do is simplify it, and it's sometimes called the naive Bayes procedure, and just to assume that even though it might not be true, to just assume a model where the x's are independent from one another given y. So that's called the naive Bayes. And that could be useful if, that might allow you to use non-Gaussian methods within each class, for example. If you want to get, there are more complicated things and probably in many cases better things to do, but here are two simple examples. So what would learning, of course, fitting a Gaussian model to each class would involve estimating its mean and its covariance. And you might assume the covariances are equal across the different classes, for example, to simplify things. And then it would just boil down to using the training data to estimate Gaussian means and Gaussian covariances, for example, by maximum likelihood, which might work okay if you have a large enough training data set and dimensions are not too high. Okay, before talking again a little bit more detail, let's just talk about what discriminative learning means. So discriminative learning is kind of a shortcut. Instead of trying to learn the whole joint distribution x of y and then computing p of y given x, just directly tries to learn p of y given x from the data. So the idea is we don't need the full joint distribution. We only actually care about p of y given x, or even just the expectation of y given x. So let's bypass the difficulty of estimating p of x given y and just directly try and learn p of y given x. So an example of a method that you probably come across that does this is logistic regression. It models the conditional distribution of y given x. And we'll also see in a minute examples that you may or may not have seen before based on k nearest neighbors. So you can think of that also as kind of trying to learn p of y given x directly from the training data. So let's have a quick look again at the textbook. So so here's their kind of toy example. So just, you know, if we wanted to take a generative approach to this, we might model the orange dots as being from a bivariate normal distribution and the blue dots from being from a bivariate normal distribution. They look a bit more, they don't quite look Gaussian in this case. They look a bit more complicated, and in fact they are. They're from some mixture, I believe. But let's just imagine, for the sake of argument, you might model each of those groups as Gaussian. You would estimate a mean for the orange dots somewhere around here, I guess, and a mean for the blue dots around here, and you'd estimate the covariance matrices. Possibly you'd assume a common covariance, or possibly you could assume a separate covariance within each group. And then, having done that, you could work out the decision rule by computing p of y given x. So that would be the generative approach. And the alternative discriminative approach would be the kind of approach that they've actually used to generate this decision rule here, which was to use a linear regression, which directly models p of y given x and doesn't assume any specific model for x. So those are two different approaches. As it turns out, both those approaches lead to a linear discriminant boundary. So the two Gaussians, the Gaussian models within each class, if you go through this math, this is with a common covariance at least, the decision boundary that you come up with will be linear. But it will be, the linear decision boundary will depend on the estimated mean and the estimated covariance here, which were being, and we were estimating those by maximum likelihood, for example, which is a different procedure, a different way of estimating them than if we use the discriminative approach. Either linear or logistic regression is not estimating the parameters the same way. So even though both of them end up with a linear boundary, it wouldn't be the same linear boundary decision rule. It wouldn't be the same line that, you know, above the line you classify as orange, below the line you classify as blue. It wouldn't necessarily be the same line because they're using different procedures to essentially to estimate that line. Let's just look at the k nearest neighbor. This next figure, figure 2.2, is showing a decision boundary, the black squiggly line rather, which is based on 15 nearest neighbors in this case. Okay, so the way this works is that for a new data point, you classify it. How do you classify it as being orange or blue? You look at its nearest neighbors. In fact, you look at its 15 nearest neighbors. So if it were here, for example, then most of its nearest neighbors are blue, and so what happens then is it gets classified as blue. It takes a majority vote, in fact, in order to estimate the most probable decision, the most probable class for a given new point. So again, for a given new point without a label, you look at its neighbors in the in the two-dimensional space. The nearest ones, the 15 nearest ones, if 8 of them are blue and 7 of them are orange, you're going to classify it as blue. And you can also think of the ratio of those things as a kind of non-parametric estimate of the probability that y is blue versus orange as well. So you might be more confident that it's blue if 15 of its 15 nearest neighbors are blue than if only 8 of the 15 are blue. So you can think of this nearest neighbor approach as kind of estimating the conditional probability that y is blue or orange by just looking at the neighbors. Right? And the conditional probability of y given the location in space is exactly p of y given x, right? So you can think of this nearest neighbor classifier as essentially estimating in a non-parametric way p of y given x from a training data set, from this training data set. You can see actually it's not a simple decision boundary here. There's a little point here that would, I think, be classified, that it would actually be classified as orange just because of the way that the things fall. So it's kind of a funny thing that can happen with, you might think that maybe that was a bad thing in this case, okay? So just to summarize, what are the pros and cons of the discriminative versus generative approach? Well, the discriminative approach means you don't have to model X, and that can be a pain, and getting good models for a high dimensional X can be really hard. So potentially makes the approach more robust. On the other hand, if you do happen to have good models for X, then you're losing the opportunity to use them. So in settings where you have good models for X, it may be better to use a generative approach. It's actually possible to use generative models to use unlabeled data. So that's another kind of nice feature. That's especially nice in settings where it's expensive to collect labeled data, but it's very easy to collect unlabeled data. So think about images that you might have hand labeled by a human. That might be expensive, and then collecting a bunch of unlabeled images could be really cheap. So that's easier to build into generative models. Yeah, you can also have a quick look at this section as well if you want more on that.